Okay, here's a thought. What if a PhD thesis, right, written in Latvian during World War II about something called osculation, basically how shapes touch? What if that actually holds some surprising connections to really cutting edge modern math, ideas that didn't really pop up for decades
It
later?
does sound pretty wild, yeah. Osculation feels very, classical geometry. Not exactly the first thing you think of as a precursor to modern abstract stuff.
Exactly. But that's what we're going to dig into today. We've got these sources bits from the original 1943 thesis by Emanuels Grinbergs, plus some really helpful modern takes on his work. Our mission is to unpack his core ideas, see how he thought about these geometric puzzles, and then uncover these fascinating links to something called jet theory in modern geometry.
Yeah, think of it as kind of a mathematical cold case. We're looking at this historical document, written under pretty specific circumstances, and finding these seeds of a much bigger, more powerful theory. It gets a bit technical, obviously, but we'll focus on those key insights, the aha moments. So it's like a treasure hunt through math history.
All right, so let's start where Grinbergs did. Classical tangency. We probably all remember tangent lines, right? Lines that just kiss a curve at one point.
Sure.
And then you've got the next level up, the osculating circle.
Right, the circle that doesn't just share the tangent, but also the curves bend. It's curvature at that point. It fits really snugly.
And Grinbergs points out this classical stuff goes way back. Ancient Greeks were already thinking about how shapes connect at a point.
Exactly, those are the basics. But Grinbergs, he wasn't satisfied with just circles or planes. His big idea was to generalize, think about osculating figures,
Right.
any shape, really. And the key example he really dug into was osculating cylinders for space curves. Now, that's a much trickier shape to fit perfectly against a twisting curve.
A big step towards a more universal idea of contact.
Definitely.
So how did he actually define this order of contact? How do you make touching precise?
Well, he thought about it in terms of how many infinitesimally close points. Two things, say a curve and a surface, share right at a specific point. And the key insight was connecting this to derivatives. If a certain function representing the setup, and its first, say, p minus 1 derivatives are 0 at that point, but the next one isn't, then you have contact of order p minus 1. It's all about how quickly the function pulls away from 0.
Okay, that's crucial. Because the sources stress he deliberately avoided using distance to define this, especially near tricky spots like singular points.
Right. Distance can get weird there.
Instead, he used parameters to describe a curve and surface and define contact just using those derivative conditions. Zero derivative, zero first derivative, and so on.
Yes, and that made his theory way more general, more robust. Plus, it didn't matter how you parameterize the curve, the contact order stayed the same, which is what you want for a real geometric property. He knew singular points were still a challenge, but for regular points, this derivative approach was a big leap.
Okay, now this is where his thinking gets really interesting. He noticed this weird parallelism, almost a duality, he called it, between two problems that look different on the surface.
Exactly. He saw that finding a surface that osculates a curve touches it really well. That problem is mathematically parallel to finding special characteristic points within a whole family of surfaces.
So, like, on one hand, you're fitting the best surface to a curve. On the other, you have maybe all spheres of a certain kind, and you're looking for points that lie on a whole bunch of them clustered together.
Precisely. He saw the symmetry. If surface A shares p infinitesimal points with curve L, then thinking dually, point X on L lies on p infinitesimally close surfaces from some family S.
You just flip the roles of the curve in the family of surfaces.
You got it. And the modern commentary talks about Pip's bundles to describe this. You can view the curve as the base and the osculating surfaces as fibers, or flip it. The surface family is the base, and the curves defined by osculation are the fibers. It's a neat, symmetrical structure.
Now, to make all this work mathematically, Grinbergs needed a solid way to measure the order of the solutions he was getting from his equations.
Right, he needed a criterion. He used an analogy. Think about finding roots of a single equation like f(a) is 0. Or root A has order r if the function and its first r1 derivatives are at 0 there, but the rth isn't. He basically extended that idea to systems of equations with multiple variables, like the parameters defining his osculating cylinder, for instance.
And how did he do that for systems?
He used a clever trick.
Yeah.
He parameterized all the variables in his system using just one parameter. Let's call it the t. So everything depends on t. Then the order of the solution to the original system is related to the order of the root t in the new equations that only involve t. It reduces the complexity.
Huh. And it's pretty amazing. He actually ends that section wondering if this whole criterion for algebraic systems could be proven purely algebraically, without needing calculus concepts like continuity.
Yeah, he had this intuition that it might be possible. And that question hangs there, and it's really significant because, well, spoiler alert, modern math does provide that algebraic answer.
Okay, that's a perfect lead-in to the next level. Superosculation. Sounds intense. What is it?
It basically means the contact is even better than it needs to be. The curve and the osculating figure touch more closely than the minimum requirement for defining that figure.
Yeah.
So more derivatives vanish than you'd strictly expect.
So if you usually need, say, n conditions met for basic osculation.
Superosculation means n plus 1 or n plus 2 conditions are met, extra agreement.
Okay. And what causes that?
Well, for instance, if an osculating surface that normally needs n1 order contact actually achieves nth order contact, that's superosculation. It often happens at special points on the curve, maybe where the osculating figure itself is momentarily stationary relative to the curve, or where multiple possible osculating figures happen to coincide.
And if the supercontact happens everywhere along the curve, not just at isolated points?
That's a big deal geometrically. It often means the curve has to lie on some specific fixed surface or maybe even multiple surfaces. It's highly constrained. Grinbergs also noted that achieving the absolute maximum possible order of contact, the highest superosculation, is tied up with singular solutions of certain differential equations, like the ones describing geometric families.
Okay, so we have the general framework. Contact via derivatives, that cool duality, quantifying solutions, and this idea of extra special contact, superosculation. Now let's make it concrete. Let's look at the big example he worked through. Finding the osculating cylinders of revolution for a space curve.
Right, this took up a good chunk of his thesis. It was his test case. He set it up using a coordinate system that moves along with the curve, the Frenet frame.
Yes, the tangent, normal, binormal directions.
Exactly. That frame tracks the curve's local geometry. He then defined the cylinder's parameters, its axis direction, its center point, its radius, all relative to this moving frame.
And he introduced these things called immobility conditions. What's the idea there?
Okay, so as you move along the curve, that Frenet frame is twisting and turning, right?
Yeah.
If you want to define the osculating cylinder at a point, you need that cylinder to be, in a sense, fixed relative to the frame. Right at that instant, you're defining the contact. The immobility conditions are the math equations that force the cylinder's parameters to be determined only by the curve's properties at that point, like curvature, torsion, and their derivatives. So the cylinder isn't sort of wobbling independently as you define the osculation.
Got it. It locks the cylinder to the curve locally.
Precisely. It connects to older ideas in the geometry of motion, too.
So using this setup, his contact definition, these conditions, what did he find? How many osculating cylinders does a typical space curve have?
He derived a system of equations, crunched through the math, and found that in the general case for a curve that's properly 3D twisting and turning, there are generally 6 distinct osculating cylinders of revolution at any given point.
6. Wow. That's surprisingly specific. I assume getting that number involves some pretty intense calculations with the curve's curvature and torsion and how they change.
Oh, absolutely. His equations ended up relating the cylinder's radius and axis orientation to rust and their derivatives. It's quite involved.
Did he look at special cases?
Yes, he did. He looked at things like helical lines. For a standard cylindrical helix, he found something curious. The osculating cylinders could actually be imaginary, mathematically speaking, which you wouldn't expect for a general curve.
Interesting. And what about degenerate cases, like if the cylinder sort of collapses?
He covered that too. For example, showing how one of these cylinders could degenerate into what he called a doubled osculating plane. So he was thinking about the edges and the exceptions, not just the standard case.
Okay, this has been a fantastic tour of Grinberg's 1943 work, but now the payoff. Where does this connect to modern math? This is the really mind-blowing part, right?
This is the big reveal from the modern analysis, yeah. The core insight is that Grinberg's whole framework, defining contact order by vanishing derivatives, the duality, quantifying solutions, dealing with special cases, it's exactly the fundamental concept behind what we now call jet bundle theory.
Jet bundle?
Jet bundles, the cornerstone of modern differential geometry, formerly developed mainly in the 1950s and 60s by people like Charles Ehresmann. Grinbergs, back in 1943, was effectively working with the idea of jets before they were formally defined or even named. He was decades ahead.
Wow. Okay, so what is a jet bundle, conceptually? How does it capture Grinberg's ideas?
Well, imagine you want to classify how geometric objects' functions, curves, surfaces behave right near a point. A jet bundle is the mathematical structure that does this. It doesn't just look at the value at the point, that's the zero jet. It looks at the value in the first derivatives, the one jet, and second derivatives, the two jet, and so on, up to any order p. So a p-jet captures all the derivative information up to order p. It's fundamentally about classifying local behavior and contact based on derivatives, which is precisely what Grinbergs built his theory on.
I remember his question about whether his solution criterion could be proved algebraically without continuity.
Yes, and modern jet theory gives a resounding yes to that. Jets can be defined purely algebraically, using tools from abstract algebra like quotient rings of functions. You don't need calculus concepts like limits to define them rigorously. It proves Grinbergs' intuition was spot on.
So how does superosculation fit into the jet picture, that extra contact?
Simple. Superosculation just means two objects agree at a higher jet level than the minimum required. Think of jets forming a tower. J at the bottom, then J, nested inside each other. If defining an osculating figure requires agreement up to, say, the Joe level, then superosculation means they actually agree up at the Joe level, or even higher up the tower, more shared derivative information.
Makes sense. And those immobility conditions for the cylinders, any modern interpretation.
Definitely. You can view those as defining what are called constrained jet bundles. You're not considering all possible jets of cylinders. You're restricting to a subset that satisfies certain conditions related to the curve's own geometry conditions that ensure the cylinder is immobile relative to the Frenet frame. This links Grinbergs' work directly to modern ideas involving group theory and geometric structures that have specific symmetries or invariances.
And finally, his link between maximal osculation and singular solutions of differential equations.
That also fits perfectly. In modern jet geometry, differential equations are often represented as geometric structures within jet bundles. The singular solutions Grinbergs was interested in, they correspond to special points or subspaces within these jet structures, places where the standard solution behavior breaks down, revealing deeper geometric features.
So, okay, let's pull this all together, this deep dive into Grinbergs. What's the big takeaway?
I think it's just a stunning example of how fundamental mathematical ideas can emerge, sometimes almost unnoticed, and then reappear decades later as cornerstones of a whole new field. Grinbergs tackled this specific technical problem of geometric contact, and in doing so, he intuitively grasped the core principles of jet theory.
Yeah, his foresight in generalizing osculation, using derivatives, seeing that duality, wrestling with the algebraic side in the singular cases, it's really quite remarkable.
And for you, listening, understanding this connection gives you, I think, a real appreciation for how math evolves. Abstract ideas aren't always developed in a straight line. Sometimes the seeds are planted long before the forest grows. And his detailed work on cylinders wasn't just a side calculation. It was vital proof of concept for his whole abstract theory. It showed his general ideas could actually solve hard, concrete problems.
From just asking, how do things touch, to this incredibly powerful structure for organizing geometry based purely on local derivatives.
It really is amazing. These fundamental concepts just resonate across time.
It definitely makes you wonder, doesn't it? If this seemingly niche work from the 40s on geometric touching could anticipate so much of modern jet theory, what other profound insights might be lurking in older mathematical texts, maybe in fields that seem, a bit settled or less fashionable today? What connections are we still missing?
That's the exciting part. There's always potentially more to uncover if you look closely enough.